So hopefully, yeah. Okay, so we have 1 minute. I think that we'll have a nice discussion for this session. The plenary session of today is composed of several talks on dark matter detection and some recent development on some neutron portal, etc. So, but the first speaker of this session is a Gray Ribka from the University of Washington. He will talk about action dark matter searches. Please.
Thank you very much. So yeah, Gray Ribka from the University of Washington talking about Axion dark matter searches. Actually, I'm going to talk about a small subset of them, the one that I mainly work on, and then ones that are kind of related, and see how far I can get through. I have a picture here, as I was saying earlier, of Daejeon, because here I am halfway around the world, and I really wish I could be there. So this is just my small taste of my memory of, well, this is as close as I can get where I am now. Has nothing to do with the topic though. So. Right, so I'll give you a brief review of axions. There's actually been a lot of good talks on axions and axion dark matter, and so I can be very brief, and maybe if I'm quick about it, we can get more discussion. I'm going to talk about how axion haloscopes work, which is a specific category. It's kind of the big gorilla of axion searches. And then I'm going to talk about ADMX, which is an example of an axion haloscope and also what I consider the leading axion haloscope. And I'm also going to touch on briefly other haloscopes and some exciting technology in the horizon, so as not to leave anyone out. Right, why axions? So this is just my favorite theorist slide because it's a plot I can actually understand, is that theories with dark matter axions are natural, elegant, and still viable, which is not true of many other things out there. So they're worth looking for. To go a bit deeper into the motivation, QCD is naturally CP violating. Just naively, if you were someone to write the full standard model of Lagrangian down, you would say, oh, I expect to see a neutron electric dipole moment. However, when we measure it, there is no neutron electric dipole moment as far as we can tell. And this suggests some very weird cancellations that can't happen by accident. However, there's a good explanation for this. Is the new symmetry is out there, the Peccei-Quinn symmetry, and it naturally and dynamically cancels everything. And the only problem is it creates a new particle. So there's a new particle out there, and that particle is called the axion. And the axion looks a lot like a pi knot. And for people in my business who are looking at light axions, the interesting coupling is axion to 2 photons, and that diagram there. It's nearly model independent. Well, I would say that classically it's model independent. You can just calculate that coupling, and there's really only a little wiggle room. And the benchmark models that kind of bound the wiggle room are KSVZ and DFSZ, though you've heard some very creative theorists earlier in this conference talk about ways that you can actually fall off that coupling. KSVZ is the more strong coupling. DFSZ is the weaker. It's inspired by grand unification. And while you can produce couplings below DFSZ, you begin to run into other fine-tuning issues, and so that's the one that's we're targeting usually. So let me talk about the broad landscape of how, when you're looking for axions and axion-like particles, you make a plot of this coupling, GA gamma, shown on the left, and the mass, which spans many orders of magnitude on the bottom there. And the colored regions show places that axions have been experimentally excluded, except for that yellow band. And that yellow band is the region where QCD axions in the classical sense that makes sense. So there's a lot of white space that's unexplored that are axion-like particles. But if you want to solve the strong CP problem in a simple way, then you want to be looking in that yellow band where KSVZ and DFSZ are. And there's a lot of ways to look for axions, both as dark matter and as other things. And so I have kind of a collection here, a very nice kind of graphic. And I'm going to be able to talk about some of these, but not all of these. There's in the US, we're doing the SNOMAS process, and there's this Cosmic Frontier Working Group #2, wave-like dark matter. And if you're super interested in what's completely cutting edge, you can look at the letters of intent there to see what's kind of up and coming. But this is far too broad a topic for this talk, so let me focus down. So if I redraw that plot of coupling versus mass, and I start looking at the types of experiments out there. I'm actually going to focus in the gigahertz frequency range, the micro EV frequency range, and that's microwave cavities for the most part. And the reason I do that is because I personally find that's the most compelling. It's not the only way you can make dark matter, but it's the most like this, if you want to be simple about it. You produce axion dark matter because in the early universe, when you cool below the symmetry breaking scale for Peccei-Quinn symmetry, you dump a lot of energy into the axion field, and this is left over as dark matter. So it's not a thermal process like WIMPs, but it's pretty straightforward, though there's some uncertainties about exactly what kind of axion couplings give you the right dark matter. And it has a lot to do with lattice QCD calculations. It has to do with whether things happen exactly before and after inflation scale. And of course, if you add new physics, you can change everything. But in general, the place to start is kind of the 1 to 100 micro EV range. And that's where it's pretty straightforward to make cosmological models where all of your dark matter is made out of axions that are made in this misalignment mechanism. So if I zoom into that 1 to 100 micro EV, and I look just in the archive over the last 10-ish years and plot people who are looking at sort of the vanilla post-inflationary axion dark models, and I just pull the numbers of the central numbers of their predictions and write them down, you can see there's some theoretical uncertainty here, and I won't even get into what it is. This is an experimentalist. You say, oh, there's kind of a couple orders of magnitude that we need to look over, and you can see there's some experiments that are starting to explore that region, and those are haloscopes, and that's what I'm going to focus on mostly. So an axion haloscope, the idea came from Pierre Sacchivi back in 1983. The idea is that this axion photon coupling can be utilized if you've got a big magnet that provides one of the photons in your axion photon vertex. And so the axion dark matter field comes inside this big magnet and converts into real observable photons at a single frequency. And you can enhance this conversion rate if you've got a microwave cavity or resonator of some sort that resonates at exactly this frequency. So at that point, you've converted dark matter into normal electromagnetic radiation, and you just pick it up like you would with a radio or something. So to be able to detect it, you want a big cavity volume, you want a lot of dark matter in there, you want a big magnetic field, so there's a lot of conversion of axions, you want a highly resonant cavity Q. That is to say, if you found that the resonance, you want the cavity to be very resonant at that frequency. And you're going to be looking for this signal amongst a sea of noise. So you want the cavity physical temperature to be very low, and you want any amplifier noise to be very low. And that's really all there is to designing these things from first principles. And I actually talk about this in my first year physics class because the principle is very simple, and that I show this demo. And this is a demo about kind of resonant energy transfer, and you have these two tuning forks, and if they're tuned to the same frequency, you whack the first tuning fork and it rings for a while, and you snatch it up, and you can still hear the ringing because the other tuning fork there has picked it up, even through the air, which is a very weak coupling. And it's picked it up because they're tuned to the same frequency. If they're not tuned to the same frequency, you get no energy transfer. And the equations of motion of an axion experiment are exactly the same. And I can say that the first tuning fork, the one where the energy comes from, is the axion dark matter field. The axion photon coupling is that weak coupling through the air, and the electromagnetic cavity resonance is where you are picking that energy up. So you just transfer that energy over in a very efficient way. To move away from tuning forks, here's a slightly more complicated cartoon showing the axion coming in. There's a microwave cavity there in a strong magnetic field. There's a tuning rod that lets you change the frequency of that cavity. That axion converts into photons, is picked up by a little antenna. It goes through an amplifier. And out of that amplifier, now you're looking at radio waves, and you can just plot a power spectrum, power versus frequency, and you're looking for a bump. And that bump says, hey, there's power coming into my cavity just from out there. And that's what you're looking for an axion signal. And that signal, of course, it's never going to be that good, but that's a nice enhanced plot there. If you want to get into the nitty gritty, I apologize, but I guess we got to show equations every once in a while here. But you can see that the things that go into seeing an axion signal, it has to do with your antenna well coupled, how big is your resonator, is your magnetic field high. There's a form factor, which is how well does the axion field overlap with your resonance. There's that G gamma has to do with the model coupling. That's KSVZ or DFSZ or something else. Of course, more dark matter density makes a bigger signal, and the frequency and the resonator quality factor come into play as well. And what's actually more important we're finding for modern Axion experiments is we can build an experiment that's as sensitive as you want at any one frequency, but how quickly can you cover frequencies? Because here we have orders of magnitude uncertainty. And so we're actually interested in scan speed. And in scan speed, the magnetic field matters a lot, the Q matters a lot, the volume matters a lot, and also getting the noise temperature low matters a lot, because the lower the noise temperature, the less time you have to spend at each frequency before you can eliminate an axion. So I'm going to tell you about my experiment, ADMX. Right now it's called the ADMX-G2 is our current incarnation. There's a picture from long ago when we didn't all wear masks. It's a worldwide collaboration, and we are looking to find the axion. And our experiment looks like this. There's a cutaway view on the left showing around an 8 Tesla magnet. Inside of that is that cavity from the cartoon. Above that, space for cryogenics and amplifiers, and the signal comes out the top. And you can see we can pull the cavity and bits from the inside, and you get a sense of scale over there on the right. There we are craning it out. Right, and so an important part of knowing about the resonator, so I'll go through kind of some of the highlights of the technology involved, is that because we don't know the mass of the axion, we have to be able to change the frequency of the cavity, and we do that by moving these tuning rods around. So it's like the microwave cavity is kind of meter scale, and we've got these tuning rods, which are kind of baseball bat sized, that move around at cryogenic temperatures, and by moving these tuning rods, we change the resonant frequency and change which axion mass we're sensitive to. So it's a matter of go here, look for the axion, move the rods a bit, look for the axions there, and just step, 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 step until you've covered the entire theoretically exciting region. Other important technologies, everything is down at millikelvin cryogenics these days to get the noise temperature down. To get the amplifier temperature down, we use superconducting RF amplifiers. They operate near the quantum limit. And then large bore high field superconducting magnets are critical for an axion experiment. The analysis is, in some ways, it's simpler than analysis from many physics experiments, because most of the time you're just looking at thermal noise. So it should just be kind of a Gaussian spectrum modified by a little bit by your filter shapes and standard RF technology. So an example here of some plots is normalized power versus frequency. So you take some raw data, you correct for the shape of the receiver, and at that point you have a power spectrum, and you're just looking for bumps. At that point, you're just looking for bumps. And you do this kind of every couple minutes. You scan at a certain frequency. You then move the rod, scan at a certain frequency, move the rod, scan at a certain frequency, combine all these power spectrums and look for bumps. And if you see a bump, well, then it could be an axion. And so fortunately, with an experiment like this, you can go back and rescan. And we go back and rescan kind of on a 1 week time scale. It's very nice, in comparison to some of the WIMP experiments where you run for years and you get a few events, and that's a sign, okay, I've got to build a one that's 10 times as big and maybe scan and go for longer. Here we just say, okay, we see a bump, let's take next week, go back and double check. So we'll know very quickly once we found an axion. And so if we do have, and if the bump is still there, we call it a persistent candidate, and we have a series of tests to see if it's an axion. And we always have these bumps because we have blind signal injection. I'll talk a little bit more about that because we've got a good one coming up here. The sort of thing we're looking for, the line shape of the axion, has nothing to do with particle physics and has everything to do with astrophysics. It has to do with how thermally broad is dark matter. And fortunately, we can set bounds on that, because if dark matter is too hot, it falls out of the galaxy, and we know that doesn't happen. And so we know the line shape, the kind of most conservative line shape, is the Maxwell-Boltzmann line shape, and that's what we usually use. However, I'd point out that in-body work, more detailed simulations, often suggests that the axion line shape is a bit narrower. A bit narrower line shape concentrates the power in a smaller number of frequency bins, and so you're actually more sensitive. So I feel like we're being fairly conservative when we set limits on the Maxwell-Boltzmann, and we also sometimes show limits on the in-body simulation to show what we think is more in line with modern astrophysical thinking. So axions are not the only thing that cause bumps. There can be potential RF interference. We're operating in the gigahertz range, so there's cell phones, Wi-Fi, TV, radio, all sort of things. And there can also be statistical fluctuations, the sort of look elsewhere effect. So we have stringent requirements for what makes an axion signal. So we can check, is the signal outside the magnet, so it's in the room? That's going to be TV or something. So we can use that to identify signals inside the experiment that are also outside the experiment, that's not an axion. An axion has to be there all the time. At least in standard axion cosmology, dark matter is smooth on scales of on human scales for sure. It has to follow Lorentzian line shape of the cavity. That's to say that it interacts properly with the resonance of the cavity. We check, does it interact with the certain resonant modes of the cavity? Because the resonant mode wave function has to overlap with the axion wave function, and it has to scale with the magnetic field, square to the magnet. And finally, if we get a signal that does all this, we can also tease out daily and annual frequency modulation. That's something we ought to be able to see. Here's an example of a test like this that we did earlier this year. So here we have a synthetic signal team that injects axion signals blindly. That is to say, they have a cable that runs to the experiment. So they're real electromagnetic signals, and they have a box, and the box is locked. And no one on the analysis team or even the operations team has a key to this box. And so this box could be putting out an axion signal at any time, or it could not. So the analysis and operations team, when they see something like this is a plot of power versus frequency, and we've lined them up just one after another vertically here, just to show how the signal evolves as we tune the cavity. The vertical axis doesn't actually mean anything. And you can see that when the cavity is sort of centered on this signal, there's a bump, and when it's off, there's not a bump, and that's a really good sign. There's an exciting signal there. If you add it all up, there's a huge signal noise 10 signal, and this is something that would be about for let's see, I believe it's a few times DFSZ axion is what would make this signal. And so we got very excited when we came across this, and we were able to exercise all of our dark matter detection tests. There on the left, we're checking, is the line shape consistent with cosmological predictions. The blind injection team did something very tricky here in that they made it not exactly right, because this got me very excited, because I figured they just, whatever the textbook line shape is, they put it in, but they made it just a little bit different, but close enough to be very excited. We found in the middle that the signal was clearly coming from inside the cavity. That is to say, we could trace out the cavity's Lorentzian line shape from that. However, within the operations team decided to do one of our very serious tests, and that is, does the signal interact with the different cavity modes as expected? The TM010 mode interacts well with axions. The 011 mode does not. An axion signal should be vanished in the 011 mode. This signal was present in both of them, and so we were able to actually catch the synthetic injection team while before we like started writing the paper, and they raised their hand and said, haha, got you. This time we were able to say, aha, all right, this is the first time we really exercised this particular axion test. So we were very excited, and it made us very exciting that yes, we have our experiments set up to detect axions, and we have a series of tests, and we've exercised them, and so when the real thing comes, we'll be ready. And so we've just released very preliminary sensitivity plots. Here's axion photon coupling versus frequency or axion mass. You can see the earlier 2018 and 2019 runs of ADMX, and with the 2020 run, we've gone much broader. I do have to apologize. Our goal is to hit DFSZ. We are not quite there yet. We're actually midway through this run. And of course, we've all suffered from the pandemic, and we had a noise temperature issue in our amplifier that we wanted to work on, but it required 6 people kind of all with their heads together. And so we said, no, we're going to run this reduced sensitivity until the university lets us work all together. And we're going to be doing that in a few months and resuming the run in the fall. However, we have searched over. So if there's a KSVZ axion in this range, then it's sitting in our data. So that's pretty exciting, as we're covering larger and larger mass ranges each time we go. Put it in a broader context, here's a coupling versus frequency or mass plot again. In this case, we've taken those model predictions and been a little bit more careful about what their suggested ranges are. And one thing we see is we're just now reaching into kind of the lower bounds of some of these 2016 predictions, so we're excited about that. But you can see there's still a long way to go, and we still have operating plans to go to higher frequencies. So ADMX-G2, what we're running right now, we hope to get all the way up there to about 2 gigahertz. It's hard to go to higher frequencies because the resonator volume gets smaller, the Q gets worse, the noise gets worse, and we have a series of we have plans to counter these with technology, and I'll go into those. So our first step is, as the cavities get smaller, we're just going to get more of them. So we'll be adding cavities together. This is similar, but not quite the same as what you saw in the presentation by CAP. These are actually fully separated cavities where the signal will be power combined. And those are built now and being tested and being ready for the next run, but that's still a year away. Furthermore, looking beyond 2 gigahertz, we've just started conceptual designs of a larger experiment based around a large volume magnet. There's kind of this pressure between, do we get a smaller magnet that's higher field or a same field but much larger bore? We think we're going to go with much larger bore, and we're at the point where engineers are making drawings. And with that, we hope to go up beyond 2 gigahertz, 4 gigahertz, and beyond, and really get into that exciting region where many of the theoretical predictions of axions are. And so that's where we are with ADMX. It's an exciting time. We're taking good data where we could find it at any time, and we're looking in more and more plausible places. I will briefly talk about some other haloscopes and exciting new technologies out there. There's a sort of simultaneous 8 hours shifted from this conference. There's the PASCOS conference, which is a very Axion specific one, and I'm trying to keep up with it at the same time. There's too much to fit in this though. You already saw a talk from Woo-Yeon Chung about the IBS CAP effort here in Daejeon. I say here, but yeah, it's an amazing effort. They've got a bunch of experiments. They're starting to set some very serious limits. They've got a chance of finding the axion out there. You might notice in yeah, I guess you saw the full talk from Woo-Yeon, but you noticed in their target area, it's the same target as ADMX. So it's a kind of an exciting race between the two of us as we're both going there because we both think that's the right place to go fishing. So yeah, you think things will really be quite exciting over the next couple of years there. Other exciting experiments to look at, Haystack. It's a small experiment, but they're demonstrating some really neat technologies. They've demonstrated the use of quantum squeezing to increase their scan speed by a factor of 2. This is something that will probably trickle its way into the larger axion experiments in the near future. There's the QUAX experiment, which is instead of looking directly for axion photon coupling, you can look for axion electron coupling, then couple those electrons into magnons, couple those magnons to photons and extract them. It sounds really hard, but they're actually able to build experiments like this. They don't have sensitivity down into serious QCD axions yet, but they have big plans and they're making their way. Going up to higher frequencies, I've kind of been working my way up in frequency. There's experiments like Mad Max, where one makes, instead of a full-on resonator, they use kind of a multiple dielectric semi-resonant system to couple the axion to larger volume structures and then focus the power and measure this power. And that is something that it's deep into its design process and magnet acquisition process that's hoping to get to higher frequencies. And I'm going through these quickly, so I hope I can finish and have time for questions if someone's excited about one. Moving the other direction, looking at lower frequencies, I've focused on the micro-EV and above range for the post-inflationary axions. You've of course heard the earlier talks at this workshop describing that there are ideas for axion dark matter at lower frequency. If you want to search for those, instead of a microwave cavity, you can use a kind of a lumped element LC circuit style resonator. There's a series of experiments like this. Abracadabra has a result out there. I believe they're in the green up the top of this plot. There's also things like Shaft and DM radio. DM radio is the word has their projections for future experiments there. They think they can get down quite low, ADMX-Like and things like that.
Great.
Yes.
There was a question for your, can you read out?
Oh, I see. How about, I've got 2 more slides. How about I just do my 2 slides and let's go back with questions, shall we?
Sure. Yeah, I think.
Okay.
Yeah.
Right. So other ideas on the horizon out there to look at. There's experiments. There's very high frequency haloscopes such as Oregon in Australia. There's also the idea of moving beyond the standard quantum limit with linear amplifiers and into actual single photon detection. And there's a very interesting paper by Akash Dixit out there talking about using like actual qubits and determining what state your qubit is in. Tells you whether or not an axion is converted to a photon. That's exciting because it's the kind of drops the floor out of what it basically redefines what noise is for your signal. And there's also still ideas out there for how do you really control these resonators or semi-resonant systems, such as the bread experiment, which kind of takes some of these dish type experiments and wraps them up. It looks like a cavity, but it's not actually a cavity because it's high frequency, short wavelength compared to the structure, but it has some kind of interesting optics that may be able to efficiently use magnet volume. So that's another one to be looking at. So let me wrap up. The Axion is a compelling candidate. It's exciting. People have been excited before, but there's more and more excited people out there. And just looking at how many talks have the word Axion on them these days is really a sign of that. We have the technology to explore the most promising parameter space for Axion dark matter, and there are people working on technologies to explore even beyond that. So it's a good time to be experimenting in Axion physics, and that's why there's a renaissance right now. And I've given an overview of a few selected experiments. There's a lot more out there that I kind of just didn't have time for. And so I apologize if yours was omitted, and feel free to shout out if you want to talk about it now. So with that, let me close and move to questions. And I think Sungwoo already has one. Okay, when you inject a synthetic signal, do you consider the expected signal shape? Then as your detector is supposed to construct that they look different. Now I think I understand the question. I think my plot shows it. Here is the this is what I was saying or rather I believe this is the issue is that on our left here we have the best fit shape and the predicted shape are different. And in this case, this is where I was saying that the injection team was using a slightly different width value, because so the Axion could be a little bit dark matter could be a little bit colder than the most generic Maxwell-Boltzmann distribution, and so we have to be able to trigger on signals that have a slightly narrower line width. So in this case, yeah, it's not exactly what I would expect, but it was close enough that it could easily be, if I came back and discovered the Axion and said, oh, the line width is this, then the astrophysicist would have no trouble explaining that in terms of that would just be information about the galaxy's dark matter halo. Did that answer your question, Sungwoo?
Okay, I think this is the end of your talk, right? So now we have questions and comments. Please leave a message for your question or comment.
If I make a comment, thank you for the great talk, Gray, as usual. You did great. I was surprised that you're very picky when you look for the signals. I would say you look for all of them. I mean, a priori, you should be prepared for a surprise, right? Depending on the width. It may fit it's a model. Those Axion models are models. They are not very solid.
Well, yeah, you're absolutely right. We have to be very open-minded about the line shape,
Right.
Especially when it comes to being narrower. When
Right.
it comes to being wider, as I mentioned, so you could imagine it being a little bit wider than the Maxwell-Boltzmann, but it's very hard in astrophysics to generate a signal much wider, because
Right.
that implies a temperature so hot that dark matter kind of falls out of the galaxy.
Mm-hmm.
And so we do go in with some priors about saying the signal ought to be narrower than this. And then, as you probably well know, as you get to higher and higher, narrower and narrower cavity line shapes, you'll become it's hard if the Axion line shape becomes commensurate with the cavity line shape, because then you don't, well, is that bump something in my filter, or is that bump something? So it's convenient right now that the line shape is small compared to our whole cavity width.
Correct. Yeah.
Okay. Can you I think the line shape is very interesting. Can you comment on the resolution on the line width as compared to the action mass, for instance?
Let's see.
Like
Variable velocity of like 200 kilometers a second, and so the line width is kind of a part in 10 to the 6.
part in 10 to the 6. Okay, I see.
Yeah, I mean, and that's just that comes from dark matter is kind of going around part in 10 to the 3, the speed of light.
Mm-hmm. I mean,
So-
experimental resolution. I mean, you are talking about dispersion due to the kinetic energy of dark
Oh,
matter.
are you asking the experimental resolution?
Experimental.
Oh, that so let's say if the Axion line shape is order kilohertz, our experiment is set up if we choose to have millihertz sensitivity. So once we have found an Axion signal, there's a whole change in how we look at it, and we start making extremely fine-grained measurements, because those measurements are what you use to find how it's changing with daily. The Earth is moving around in a circle, and so the frequency will jitter just a little bit, and you need that high resolution to fish that out. But that's just a matter of what's the most efficient way to run your receiver.
I see.
And we actually have a whole second channel and analysis team that's devoted to looking for kind of more exotic astrophysical models. So if you like dark matter caustics, those actually would produce ultra narrow signals that are also that would be much better signal to noise, and we have a team that looks for those specifically.
I see. So it might be more important to find the bump in your signal first and then scan around that range.
Yeah. I mean, the hope is that if we make this discovery, there's a whole rich amount of astrophysics for everyone to do with this signal.
I have two quick questions. What is the average magnetic field you have, and what is the noise, the JPA noise you have?
Let's see. So in the latest run, the average magnetic field is around 7.6 Tesla. With a little bit, we actually end up tune the current of our magnet to try and optimize magnetic field cancellation at the location of the amplifier. So you want it as high as you can, but you don't want to actually have flux intrusion into your amplifier. And we're let's say very preliminarily, we're looking at a total system noise in the spring of around 600 millikelvin, which is a lot higher than we were aiming for. But this is the situation of, like, it's a pandemic. We can't get everyone around, we can't pull the thing out and do work on it. So that's the reason we did a kind of a quick scan for the spring. And then we hope to get down to, more like 300, 200 in the fall.
Thank you.
Okay. Are there more questions or comments? I think we have some discussion. Maybe the talk time is a little bit shorter because of online talk. So we want to have more time for discussion and some time between the talks. Okay, so I think let's thank the speaker again, the Gray, for your nice talk.
Okay, so I should stop sharing and let the next speaker prepare?
Sure.
All right.
Okay.
Thank you very much for having me.
Okay, thank you. So then let's move on to the next.
Oh, I thought did Rick have his hand up?
Okay, did I?
Oh, I was trying to applaud, sorry.
Oh, okay.
Okay, so the next speaker is Maxim Pospelov. So maybe try to share your talk slide. Okay, so I can see you. So we still have some time, about 7 minutes before your talk starts. So if you have something to discuss, you can discuss. I think I can see your talk slide well. Okay.
Right.
So how are you, Maxim?
I'm all right, surviving.
Okay, so I see you working actively on the Korean project. I saw some papers with Korean and also many other things, but
I should get more involved. I'm interested in the new underground facility that's going to be built. This type of stuff.
I see. So how is the situation in Minnesota? Do you go to the university?
The state did relatively well compared to the rest of the United States, but yeah, the university is still not much populated, I should say. But here in the Twin Cities, I'd say maybe 75–80% of the population is vaccinated. So, and the rate of infections is shrinking quite fast. So I think the real question is whether this sort of vaccine immunity is going to last into the fall, and what's going to happen in the fall. That's the question everyone has.
Okay. So maybe from fall, maybe hopefully we are going to the lecture room and talk to students.
Yeah. And travel, right? So there's been.
Can you travel within US?
You can travel within US. Well, people also change their habits. They don't go as often as they used to. Most of the seminars are still
online.
Online. Right?
Yeah. Yes. Okay. Yeah, everything is online, and I was able to invite more easily speakers from outside, from Europe and some US.
Well, the only thing is that you have to, warn your speakers about the time difference and so on, right? So
yeah.
So
sometimes I lost the speaker because I asked for 4 p.m. in Korean time, but then he realized that he thought that it will be in his time, so that things
quite a difference. Yes.
Yeah. Okay. Hopefully we will see each other in the near future.
Absolutely.
Live discussion.
Yeah, it'd be great.
Okay. So we have a series of papers about this neutron portal. So you come up with the new portal models. I remember you have also hydrogen portal some time ago.
Well, that's part of it.
It's
right?
a part of the neutron, I see. Okay.
It's
and also I realized that there are many
for a lack of better name. That's what it is.
Okay, so we have 2 minutes.
And the talk is what, 30 minutes or 35?
We have 30 minutes.
30 minutes.
We have a 40 minutes between the talks, but 30 minutes for the talk and 5 minutes for discussion and 5 minutes for preparation. I don't know. But I think
Yeah.
There is
Right.
no time for preparation for us, so maybe 10 minutes, maybe this for discussion. So,
Okay. Very good.
so I will give you a warning. I thought that at 30 minutes, but I think the 25 minutes. But I don't have to give a warning in the previous speaker.
Mm-hmm.
Yeah, but the 30 minutes for talk.
Okay.
If you are getting late, I mean, running over the time, I can give you a warning.
Yeah. Sure.
Few minutes before your talk ends. Okay, now we are almost on time. So let's move on to the next speaker, Maxim Pospelov from the University of Minnesota. He will talk about neutron portal.
All right. Thank you very much. I hope you can see my slides and hear me well. It's a pleasure to be with you, although virtually. So in the last few years, I on occasion worked on the topic that can be called the neutron portal, together with Dave McKean and Nirmal Raj. And today I'm going to discuss some physics relevant for this issue. Well, I start with a broad look at dark sectors that has been the activity that's been brewing both in the US and Europe and elsewhere for some time now. And I will try to put this neutron portal idea into a broader context. Then I will discuss an exotic situation when the proton is a stable particle, but the hydrogen atom is not, and what kind of constraints one can impose from the existing data. And then we'll describe some cosmological bounds on this model that are there and easy to pick. And then we'll finish with a more controversial topic, as that is neutron star bounds on mirror neutrons, and that is the new heating mechanism of neutron disappearing into mirror neutrons that exist for neutron stars. All right, so here's like a complicated slide about the dark sectors. So let's imagine we have the Stern model. This is the first line here. That consists of the Stern model Higgs field, fermions, engaged bosons, all in red. Okay, so if there is new physics, something like, say, heavy supersymmetric particles and so on, they can be integrated out if they are really heavy and outside of a collider ridge. And then we have corrections to that picture from, well, starting famously from dimension 5 operators, but at dimension 6, we have a plethora of new effects. However, if we have a new sector that contains in principle light particles, such as Gray just discussed, we would have to add them on to our theory explicitly. And here it's done kind of in a generic way, where in blue there are new particles, new light states, the lighter than this, or at least comparable to the Stern model, coupled to the Stern model fields. And this is sometimes called portal couplings. And we now pretty confident that we understand most of these couplings. Plus, this dark sector interaction can be complicated, and of course, the name dark implies that they might have something to do with the dark matter. And indeed, many models do include dark matter here. So the classification of this portal couplings, that is the couplings between the Stern model and the possible new light fields, is well known. There is a Higgs portal, there is a dark photon portal, which takes the two field strengths, photon field strength and the extra U1 field strength, and combines together into a gauge invariant operator. These are all sort of dimension 4 and lower operators, so we have to start from the lowest dimension. This is probably the most interesting or the most famous portal that takes a composite fermion LH and mixes it with a new fermion N. So when the Higgs goes to its wave, that creates a coupling between the active neutrino and the new end state, which can be called the right-handed neutrino. And that, we believe, might be behind the reason of neutrino mixing and masses. Then going to the high dimensional operators, there is, of course, a very famous portals associated with axions. So here it's the derivative of an axion interacting with the axial current, which I should say includes Chern-Simons current, so that Gray's coupling is also there. All right. There has been a lot of activity on trying to map the parameter space of all these dark sectors, just because they're very simple and accessible not only to the LHC, but also to the low energy experiments. So here is the mixing parameters, epsilon versus the mass, constraints on the dark photon couplings, and if you have additional matter charged under this U1, this could be very well be a dark matter. And here is like the simplest diagram of electron interacting with this new chi fermion via the mixed A prime propagator. And the investigation of this dark sector parameter space is an active field of research at the moment. Now, does the and I already said well, there's a lot of investigations for the Higgs portal and for the Axion portal, and of course for the sterile neutrino portal or heavy neutron lepton portal. Now there is well, there are more particles in nature, right? So I can ask the question if there is maybe an analog of the neutrino, heavy neutrino mixing parameter for neutrons. So imagine that you have a neutron state and you want to go through some sort of term in the Lagrangian into the new state, which I call Bion's thermal fermion, quite generically. Of course, due to a composite nature of nucleus, this is a high dimensional operator because you would have to join 3 quarks to get to this fermion chi. Or if you think of this fermion being some sort of a mirror neutron, then you have three primed quarks on the other side, which means that this is even higher dimensional, more higher dimensional operators. So just counting dimensions and understanding how they scale, this is a 4 fermion operator, is dimension 6 normalized on lambda squared. And this is obviously a high dimensional operator. And then the point is that they can be all made UV complete above the electroweak scale, okay? And so therefore, I could hope for the sort of LHC-related signatures, but I can safely stay at low energy and try to fish out the consequences of the neutron portal at low energy. So if the new particle chi is very light, for example, much lighter than the neutron state, then we more or less understand what would be the best probe of such thing. Proton can go to pi and the neutron at no cost, and then the neutron, if it mixes with a very, very light fermion, then of course it will generate the decay of a proton into a pion and this new chi state, and that is severely constrained or strongly constrained from the best limits we have on the nucleon decay. But if, sorry, here the signs are in the opposite direction. If MK is larger than Mn, then it's not obvious that if the model is constrained at all. But very interesting situation is when the splitting between the fermion and the proton becomes small. If it becomes smaller than 1.8 MeV, then no neutrons in any of the stable nuclei can actually decay into a chi state, and therefore the nuclei are stable in that situation. But the neutron, free neutron, can still decay in such a state. So then if we bring the mass splitting even further to sub-eV, then chi can be called a mirror neutron, and quantum oscillations of this of the free neutrons and chi's are expected. And so the goal is to investigate the parameter space and identify most interesting physics. So motivations for studying neutron portal can be sort of summarized as follows. It's economical new physics with implications for high and low energy physics experiments. It has the model has a shared baryon number, if you like, because the chi-n mixing, and that provides interesting possibilities for baryogenesis. Well, on the other hand, also the new fermion could be stable, in which case it's an appealing dark matter candidate and the mass close to a nucleon mass, maybe behind the fact that rho dark matter is on the order of rho baryon, that in many other models is a complete accident, right? Often is a complete accident. Well, there is, one should expect new effects in cosmology where neutrons are, and astrophysics where neutrons are crucial. Neutron stars and Big Bang nucleosynthesis, for example. And then, of course, one should expect novel effects in neutron physics, new neutron decay channels, oscillations, possibly, oscillations into dark states, and oscillations back regeneration. So this is a very, once we accept that there is a possibility of a state chi not too far from the mass of the neutron, then suddenly a lot of interesting possibilities open up. So, and my motivation to study this is to, well, the situation is very different for dark photon, where the model is studied in many decades of masses, from really as light as the Hubble scale to multi-TeV scale, and down to the really tiny couplings. And aside of some interest and a few occasional works, there isn't being a complete map out of this neutron portal, even though it's also if you like, could be an economical model, mass of a dark fermion and neutron dark fermion mixing angle. Although, of course, this is a high dimensional operator, as I mentioned. All right, so my interest was picked by the papers in 2018 by Greenstein Fornal, by Zurab Bereziani and his earlier papers that sort of they were provocative in the sense that they were trying to actually draw attention to which is of course well-known fact, the difference between the lifetimes for neutrons measured in the bottle experiments and in the beam experiments, and the speculation trying to provoke people to think is that maybe there is a shortening of the lifetime in the bottle because there is an additional decay or oscillation channel that leads to the disappearance of neutrons, while in the beam you actually perform an experiment looking for the appearance of the proton, right? So therefore these two things may not necessarily be contradictory, but you need some sort of a percent correction of the lifetime due to the new decay mode. I'm not sure that this is still a legitimate explanation, because there is an independent measurements of G sub A coupling say neutron polarization measurements, neutron decay correlation measurements, but let's leave it at that and just use it as some sort of a initial motivation. So Greenstein and Fornal also showed how these models can be UV complete, and the UV completion can be achieved with particles that are in tens of TeV and therefore outside of the collider reach, which is very nice. So if you have a model like this, so you have a neutron, you have a new chi fermion, and there is a coupling mixing between a neutron and the chi, where delta is the parameter, and you can sort of expect that a neutron can emit a gamma and decay to chi if it's lighter, and you get correct the lifetime if this is your choice of parameters. If the mixing angle is 10⁻⁹, the mixing angle is here, and the splitting is on the order of MeV, And the prediction is that you should have a sort of a gamma line of some sort, and so there was a super speedy measurements performed by our nuclear colleagues that tried to, within like a month or so after the publication of a Greenstein-Fornell paper, to try to actually detect these gamma lines, and they haven't seen anything, so they can put meaningful constraints. There is also, if the branching is that large, there is a quick sort of equilibration of n and n primes within a neutron star with some interesting consequences for mass radii relations, but I won't go into that. So the first topic I wanted to discuss is the situation where m chi is smaller than mass of the proton plus of mass of the electron, but not much smaller, so within an MeV or so. In that case, the hydrogen can decay to a new fermion plus a neutrino, but the proton itself is stable. So this is say the dark fermion, and this is neutrino. This is a completely dark decay. So this at first it looks like a hydrogen disappearance, and this is a very sort of pessimistic signature because there's a lot of hydrogen. However, if it's a radiative type capture, when the electron emits a photon, goes to chi, then you can capture this photon, and if it's energy in hundreds of keV, and it cannot be like 10 MeV, because then you have much better probes through nucleon decays. But if it's in 100, it wouldn't necessarily be in 100 keVs. And the best experiment to look for it, that the experiments would contain a lot of hydrocarbons and a low threshold and be very clean. And that brings us to a Boraxino experiment and also Boraxino test facility, whose results can be used very effectively to limit this possibility. So I'll just skip that. So one can calculate in a simple model in terms of the mixing angle and the Q value of the transition. One can calculate the spectra and the probabilities of transition, and using the Boraxino data set a very strong limits. So this is a plot with limits on this mixing parameter space 10⁻10. You can see that this particle very much degenerate with the neutron, but neutron still can decay to that particle in the gamma. So here is the constraints from this nuclear experiment looking for the neutron decays that I just said. And here is the new constraint that we can impose using the Boraxino results. Over here, there is a deterioration of constraint because the lowest part of the Boraxino spectrum is covered by the a very large carbon-14 background, as is well known. Very well, so one can turn it around, this radiative decay, and ask the question, what is the constraint on the lifetime of hydrogen atom itself, right? Because in this within this model, the hydrogen atom is unstable, and sort of depending on the model, we discussed several, you get to the benchmark of sort of 10 to the 30 seconds, and that's the constraint you can impose on the from the Boraxino data on the possibility of hydrogen decay due to the neutron portal oscillation into a light state, and that's fairly strong. It's only maybe 8 orders of magnitude or so inferior to the best constraints on the proton decay data from Super K. Very well. Well, it's interesting that all data sort of the the sensitivity deteriorates when you go to the low sort of smaller and smaller Q value. At certain point, the hydrogen becomes stable, and the chi can indicate to a hydrogen and some energy, or electron, proton, and a neutrino. And then the interesting question is how to probe that thing. And right, before I go there, I just want to discuss a really sort of very speculative possibility that if you have a hydrogen that undergoes this transition into a dark sector, the dark sector can be very, very complicated, and this subsequent fate of this particles chi can lead to the decay, the scattering, and so on. And because you have a large amount of hydrogen in the sun and on the Earth, you can actually estimate the maximum fluxes of these particles that you can expect out of this hydrogen decays, including this bound from Barexina. And you get to fairly sizable fluxes in principle as maximum fluxes, which could be used to explain some unexplained excesses, for example, in dark matter signal. But this is very speculative. Now, I'd like to discuss cosmological bounds. The point here is that early universe will lead to new bounds on this portal. The neutron to chi can interconvert, and because it's a high dimensional operator, this interconversion is shifted towards higher temperatures, higher energies, and it occurs much faster there. So therefore, you may expect actually an equilibration at early times. And then subsequent decays and inverse decays do interesting things at the time of the CMB and Big Bang nuclear synthesis. And that's an observation that allows to limit this model quite well. So I just want to show a slide on Big Bang nuclear synthesis, where the universe evolves from, say, 0.1 second to 10,000 seconds, and in the course of it, helium-4, helium-3, deuterium, and lithium-7 are cooked up. The most important epoch, well, one of the most important epochs is just under 1,000 kilo electron volts, where all the deuteron bottleneck ends, and the neutrons are rapidly uptaken by nuclear reactions. So at that point, the neutrons, the universe exists in the neutron starvation regime, and any new addition of neutrons will be felt by their incorporation in deuterium, which is now very tightly constrained by experiment and agrees between the theory and experiment. So in principle, if you have a chi fermion very close in mass to n, there could be an inverse excitations where the thermally the gammas will overcome the Boltzmann barrier and they excite chi's into n's, and that will end up in extra deuterium, for example. So this is a very powerful probe, and we try to put this together as various constraints. You can recognize this Borexina constraint and the gamma line constraint on this side, on this corner of the plot. This is a plot for MChi here below to the left of this solid line that is lighter than the neutron. So there are new neutron decays. And here above this solid line, it's a chi that is heavier than the neutron. Okay, so there is the CM, and here we also furthermore assume that this, in this plot, that this is a dark matter abundance is saturated by this chi particle. So we get constraints from various things such as nuclear stability, beryllium-9 stability, from direct laboratory constraints, from excess deuteron, and also from chi decaying at later times to electron positron, to electron proton and the neutrino, and electrons carry some energy, so they lead to a generation of extra ionization during the CMB, which is a well understood process and used in many places in particle physics as a constraint. So therefore, then this dotted line here, or dashed line rather, this is where you expect 1% correction to the neutron lifetime. And apart of a tiny sliver of parameter space, all the rest is, I would say, disfavored by cosmology. There is also a constraint from the coldest neutron stars, which I'm going to discuss shortly. Also, interestingly, there are constraints on chi particles that are heavier than the neutron, and that's because in that regime, these chi particles can decay to a neutron and a gamma, and that is again felt via CMB. Or if this happens at early times, then it's felt by the deuterium overproduction. We have also varied the abundance of these chi particles, and these limits do not, they modify, they shrink, but they do not disappear. At 1% from the baryon abundance, there is still plenty of parameter space that we were able to exclude. And I should emphasize that here in the white, this is a viable dark matter parameter space. Okay. Now I'd like to get to the perhaps the last topic that I wanted to discuss, and these are the sensitivity to all these models that occur at a really small mixing angle through the coldest neutron stars. The interesting point here is that there is a new mechanism for generating energy if there is a neutron portal, and the transition from N to chi is very slow. And now let me call this chi as a mirror neutron of some sort. So I wanted to illustrate the physics of how the energy is generated by making an analogy with the electron capture in atoms. The next speaker, Richard, has worked on various dark matter detectors, where in germanium, if you look at the spectrum, you can see the structure of the lines that occur due to the electron capture on nuclei. So if you picture the electron shell, atomic shells as a closed shells with all levels filled, then at some point the nucleus eats an electron and spits out a neutrino into the void, and then you have a hole in your electronic shells that are filled either by photons or by new electrons coming in, sort of jumping down, while the other one is ejected with energy equal to the energy difference between these two levels. This is a well understood, observed effect in atomic physics very well. So if there are mirror neutrons whose Fermi C is not filled up, and that occurs when the conversion rate is very small, then you can have a situation where in neutron stars, in old neutron stars, where the temperature is sort of already small, you can have a possibility of two neutrons scattering, producing a third neutron that is thrown above this Fermi energy, while the mirror neutron dives down. So this way you created a new neutron above the Fermi energy quite a bit. And then you also created two holes on the place of the original neutrons that are being filled up by neutrons from above, and that generates energy, which provides a new potentially interesting heating mechanism for neutron stars. This mechanism was pointed out in a nice paper by Goldman, Mahapatra, and Nusinov, and also discussed by Beregiani and collaborators and by us in these papers. So we have decided to have a closer look at what constraints on neutron to mirror neutron oscillations one can impose using the neutron stars. And here is like it's the very same model. Basically, it's now though instead of chi, I call it n prime, just to be in line with the mirror neutron literature. There is an off-diagonal matrix element here for the mass matrix, and this is called, what in my previous slides was called delta. There is a delta E parameter, which in a vacuum is, let's say, it's close to 0, but then for a true mirror situation. But then inside the neutron star, the neutrons modify its forward propagation, and there is a mass shift as a result of that, if you like. So we have taken into account this scattering processes in the star using the neutron-neutron scattering and neutron-proton scattering, which turns out to be very important, even though the protons are believed to be not more than 10% of the nucleon content. You get the heating rates that are sensitive, very, very sensitive to the off-diagonal matrix elements. And basically, in the old neutron stars, there is a relation between the oldest neutron stars are believed to be cooling off from the surface emission, and there is you can sort of relate their minimum temperature with this new heating effect that produces n primes while emitting at each collision EF amount of energy, and this I should have I forgot a very huge number here, the number of neutrons, but you basically you equate the two rates, and you get the connection between the minimum temperature and the fundamental parameters of your model. So looking at this is from our latest paper with Nirmala and David, looking at the coldest neutron star reported in the literature, whose limits on the temperature are at the level of 3000 kelvins, you can set a very, very strong bounds on the possible off-diagonal matrix element at the level of 10⁻17 electron volts. Above this level, basically, you cannot set any limits because the conversions will occur very quickly, and maybe there are some other limits, but not the ones that we have considered. You can also contrast it with limits on this model in the laboratory, and here there is a constraint on the neutron to neutron prime oscillation limit, which I have contrasted with a limit we derived from this coldest pulsar. There are other pulsars that are not as cold, and they also can be used to constrain this model. So this is the interesting development, I think, of already using the astrophysical observations to constrain the parameters of neutron portal model. Very well, so I think I'm on time, so I'm just going to finish by concluding that the exploration of the neutron portal can be viewed as sort of an integral part of the overall exploration of dark sector models, where new light physics is added to the standard model. Well, it's compared to the rest is relatively underexplored, and given that the model is relatively simple and can be formulated in terms of the mixing angle and the mass, it needs to be further explored. That's, I guess, the main message from my talk. Well, we done a number of sort of forays into this topic, and in particular set some relatively strong constraints on this model using the radiative hydrogen decays in a lab, or cosmological decays of these chi particles into the protons and electrons at the latest stage, and also from Big Bang nucleosynthesis. And new constraints almost entirely exclude the, I should emphasize, the minimal model or that tries to use N to chi gamma decay channel correcting neutron lifetime. And if hydrogen can decay to chi, typically the Boraxino experiment constrains the lifetime of the hydrogen atom to be at 10 to the 30 seconds. I find it amusing that nobody has ever thought about the life, or not deeply, I don't think, about the lifetimes of the hydrogen atom. Well, it's simply because in most models, proton will decay, right? So you don't need to think about the hydrogen atom too much, right? But in this tuned situation, if you like, there is a possibility of hydrogen decay, and we get this type of constraints. Now, I would also say that end-to-end prime conversion offers an interesting heating mechanism for all neutron stars, and taking the existing Astor bounds as that face value brings the constraints very close to what can be achieved in the lab, actually. But moreover, it will be valid for the splitting in vacuum for arbitrarily varied within, say, MEV, and while in the lab, you would have to have almost exact degeneracy. That's it. Thank you so much.
Okay, thank you for your very interesting talk and comprehensive analysis. I think there are many questions.
All right.
So you can answer question by question.
Oh.
From Doki first, maybe.
So what should I do? Stop share, or?
No, you can check the Q&A. You can click on Q&A.
It
on your
doesn't click.
screen.
Yes.
Yeah, there are 3 questions.
Yeah, I don't. It doesn't click in my case. That's
so can I? Do you want me to read it?
Yes, please.
From Doki ask question. From the UV point of view, how does the dark neutron share the baryon number? You talk about baryon number sharing.
That's a good question. So I'd be perhaps provocative and say that this is a matter of convention. If you have a right-handed neutrino, you can say, all right, my right-handed neutrino doesn't have any lepton number whatsoever. Then the Yukawa interaction breaks the lepton number, right? Or you can say, all right, the right-handed neutrino actually carries the lepton number, and then if it's a Dirac neutrino, the lepton number is preserved. So it's in some sense, what I'm trying to say, there is a possibility here of merging 3 quarks and forming a different object, which is not in the theory, right? So in that sense, initially this baryon number at high temperature will be equalized according to statistics, between the sky states and the baryonic states. That's I guess what I wanted to say.
So the next question, Jon Kerstin, could you explain again what happens when neutron star heating happens too fast for large N prime mixing? If heating happens too fast.
So that goes back to this. It's not even in my papers, but I can put some references. I think it's here. this series of papers by Anne, Dave, Sanjay, and others. So basically, when the transition is fast, these neutrons will like to go to chi particles very quickly. Now you get two fluids that equilibrate. There is a chi fluid and there is N fluid. The tricky part is that if there is no additional pressure mechanisms in the chi sector, then in that case, this model seems to be incompatible with observations because there is for various input equations of states, there is a connection between the radii of the neutron stars and the masses of the neutron stars. And if you have transferred, say, half of the energy into the uninteracting particles, chi's, then there is a problem for neutron star observations. That can be overcome, however, if there is a new mechanism that generates extra pressure. So if the skies are also charged under some new U1 prime, then there will be a repulsion, which was mentioned in this paper, for example. So I don't think it's a settled issue whether all of these models survive these constraints, because nobody has actually. So these papers analyze this, I think, in equilibrium, but how this approach to equilibrium occurs and what are there any further dramatic consequences, we don't know. Right?
So yeah, there's a short question before we finish this talk. So what is the update on neutron lifetime, battle versus beam? Hyungdo asked. Hyungdo Kim asked.
I think well, it's a high drama. It's a complicated topic with community first not believing the bottle results, now more or less converging to the St. Petersburg, closer to St. Petersburg value. Now there are some ideas what can go wrong in the say beam experiment, but this not being proven by any case. And also the new generation of the what's called the asymmetry, parity violating asymmetries in the decays of polarized neutrons. It seemed to give G sub A that is consistent with the bottle experiments as opposed to the beam results. So I'd say the jury is still out.
Yeah, I think that we are running out of time, but there's one more question from Youngda Kim. I think bound state beta decay of free neutrons not yet observed. Detecting which could help to understand your analysis.
That is correct. So in principle, one can try to get to the same model by studying the nuclei where I forgot their proper name, baryon nuclei or something, where there is a neutrons in a far above sort of the main nucleus, and sometimes they decay due to the beta decay rather than just being shed through strong forces or some collisions. So that would be the exact nuclei. It's in the family of light nuclei, and I apologize, I don't remember exactly, but this could be a way of getting on this model as well. Yes.
Okay, I think that we are running out of time. So thank you, Maxim Pospelov, for your nice talk. Okay, let's the next speaker is Richard Gates Kell. Can you try to share your screen? Okay, so maybe you can make it. You can make it to the full screen.
Is that visible now?
Yes.
Good.
So yeah, dark matter. The next speaker is Rick Gates-Kell from Brown University. He will talk about dark matter direct detection experiment review. Yeah, please go ahead.
Well, thank you so very much for the invitation. I'm so sorry that I'm not able to be with you all in person. I've added a couple of notes about myself just so I can provide some context. But what I wanted to, obviously, was invited indeed to talk about is the status with direct detection experiments. And this is something I've been directly involved in for over 30 years. So I'm going to give you some historical perspective, but also primarily make sure that you are fully aware of where things stand right now and where we're going in the future. So if the SI unit for ignorance is the IDK, then of course, as I think we have to admit, we are still at a level of 950 milli IDK. I don't knows. It's extraordinary that although we have this label for dark matter, we still have no idea what the actual composition is. Yes, we've been updating, with ever increasing accuracy, the percentage in terms of the component of the universe, but in terms of the actual composition. Now, I've been trying to work on this issue of composition for over 30 years. Now, we've cycled through a whole series of technologies, and also, I will say, cycled through a whole series of wardrobes. One of the early experiments that I was, directly involved in was the CDMS-2 experiment, which we operated at the Sudan mine, which has since shut in Minnesota. That was then I moved over to Italy, where you have to have an entire change of wardrobe. You have to brighten everything up a little bit in Gran Sasso, working on Xenon 10, and then more recently, I've been directly involved in the LUX and the LZ experiments, which are happening at Sanford Lab. Or LUX happened, finished, and LZ happening at Sanford Lab. As you can see in Sanford, we have to wear a different kind of clothing again, being in the great state of South Dakota. But of course, that may seem a little parochial there. I mean, dark matter is taking place all around the world. And as I'll show you in a moment, I actually list every one of the active dark matter experiments in terms of, direct dark matter, particle dark matter detection. And I assume you will actually be rather surprised by the level of activity. I just got back from the Sanford Lab, where we are have the LZ experiment located. For those of you not familiar with where Sanford Lab is, it's in South Dakota, as indicated with the star. The lab is relatively new. Just in the last 10 years, we went from a point. This was a visit we made to the lab just after we pumped all the water out of it down at the 1 mile down level, and of course we converted it into what you see here in the space of a year. And since then, we've been very actively using it. Now, again, SURF, the Sanford Underground Research Facilities, is one of multiple labs. With respect to dark matter, it is quite clear as we've grown in understanding concerning the specifics of backgrounds, even with fairly large or really quite large experiments, it is possible to do them at a range of depths. We don't appear to have hit substantial limitations on any of the experiments with respect to depth, except for at the very most shallow labs. In terms of the technique, and this is almost the entire duration I've been working on the experiments, we have just simply been looking for recoil spectra primarily in nuclei, although as you'll see in some of the subsequent slides, we also now search for particle interactions through electron, direct dark matter electron interactions. The first experimental results paper that came out was all the way back in '87. It does illustrate very simply the way in which we've been employing the technique. As you see on the right here, it's a conventional germanium ionization detector. At that time, the background that you could achieve was about 1 count per keV electron equivalent energy per kilogram per day of the detector. And as you can see in this case, there was a significant buildup of backgrounds below about 20 keV, which was actually due to intrinsic backgrounds within the germanium. But nonetheless, one could use that spectrum to place an upper limit on the dark matter rate. And on a log graph like this, dark matter recoil spectrum is essentially a single exponential. So you can just place a sensitivity limit as indicated by the blue graph. Now, one of the things that's happened over time was, we've had to scale up the mass of detectors. Now, at the time I was working as a graduate student in the late 80s and early 90s, this particular detector, which weighed only 12 grams, was considered to be a very exciting dark matter detector. The main thrust of dark matter detection, of course, we're getting very similar. One of the things I find incredible is we're getting very similar performance in terms of energy sensitivity and in a detector that's now sort of 10 tons rather than 10 grams. It gives you this first sense of how many orders of magnitude we've been through. 6 orders of magnitude in terms of scaling. Now, it is fair to say that actually this type of detector I'm showing you here, or ones not dissimilar from it, in fact, are opening up today new areas of dark matter searches, specifically where one's looking at very small energy quanta for looking for much lower energy lower mass dark matter particles, where they're down in the MeV, and therefore you have to work quite hard in terms of designing your detector to see very small energies. But I'll make that sort of distinction a little bit more in a moment. So I'm just covering those experiments which, in terms of this next summary table, in terms of recently completed or last few years, and some of the future ones. It's not completely exhaustive, but I tried to get as many in there. And also the dates are based on what collaborations, last time I spoke with them, had mentioned that they are hoping to implement those those deadlines, as you know, with experimental physics. So that's the sort of the complete list in its entirety. It's probably quite difficult to see on the Zoom. I think even if we try rotating, it still really doesn't fit. So what I'm going to do is I'm just going to zoom in on specific areas of that table and sort of give you an idea. So let me do that in a moment, but I just wanted to sort of start summarizing a few points that I'm going to make. As you'll see, historically, we have essentially gone through a number of different technologies, and within those technologies, you have to be ready to sort of scale them by order of magnitude on a fairly regular basis. This is demanded by the particle physics. We are having to cover an enormous parameter space, and only by being able to and being ready to substantially, take any promising technology and start implementing it, in masses. We have also seen, and it is very necessary in a field like this one, to look at the sort of condensed matter physics or the behavior of a number of different targets and to innovate. I think, specifically the C3F8 development, for instance, was a very was taken through to a very sort of promising and large mass implementations I'll show you in a moment. But also some of the innovations have related, for instance, to using the Luke-Neganoff effect within semiconductors at very low temperatures in order to make a substantial boost in one's ability to essentially see very close to single quanta electrons, but reading them out through their phonon signal that is generated as they move in a high field. And then, of course, we've seen, for instance, skipper-amp CCD technology, where you're able to co-add or continually sort of add the charge measurements by a specific style of skipper readout, which has led to an extreme reduction in the effective readout, so that we can now see single 1, 2, 3 electron signals in the in these devices, and you'll see there the implications for dark matter searches. We're also seeing a lot of interest, which is converted into experimental work now, for instance, in using light nuclei, again, targeted more towards the MEV rather than the GeV dark matter or WIMP, style searches. Now, I will also say, having worked on at least 5 technologies pretty seriously, technologies come with problems. I like to discuss those in terms of a Sisyphean index. Sisyphus, of course, who was cursed to carry a rock up a hill and only to have it roll down, and to have to repeat the same process. And I can tell you, working on certain technologies, it's felt a little bit like a Sisyphean job. I'm in the 33rd year of looking specifically for dark matter. And as I've mentioned before, we're now about 6 orders of magnitude beyond where we started. Now, I will, the technologies that have worked well just sort of want to work, and have as such a low Sisyphean index. It is, there are a number of technologies one can work on that don't want to work, and one has to be ready to, should we say, to admit defeat sometimes. But anyway, I'll give you an idea of one specific technology I've been working on for the last 10 plus a bit more than that now, 15 years, which has gone rather well, but I'll show you that in a moment. This, of course, is a plot of the sort of Moore's law relationship, just in terms of the transistor cost or transistor density. Just to give you a sense of scale, that's a factor of 10 every 6.5 years is the Moore's law. Now, if we instead look at dark matter detection on the standard sort of cross-section scale, we confine ourselves to a single mass for the dark matter particle. It is actually possible to just compare all of the cross-section limits. And what we've seen is that initially there was a period of using double beta decay, conventional germanium ionization detectors, including the one I showed you, or the graph I showed you at the beginning, which somewhat extraordinarily was actually conducted, barely 10 meters from where I was sitting in that photograph at what is now the Sanford lab, used to be known as Homestake. But we have the LZ experiment located there now, and so what happened in the 2005 region was purpose-built cryogenic detectors with discrimination were used to great effect, and at the same time very large mass sodium iodide detectors came on, very specifically the Dharma and Libra, and I'll talk a bit more about that in a moment. But also what we saw was an introduction in the 2000s of a liquid xenon detector technology in Zeppelin and xenon, and latterly in Lux and LZ. And as you can see from the vertical scale, we managed to push many orders of magnitude down just using that one sort of primary technology. And we've searched, over 5 orders of magnitude, getting on for 6 now. And if we take the Moore's law and just put it on the same plot, you can see that we've actually been beating it. And I just sort of say this because in order to meet this kind of parameter space sweep, it has been necessary to move as rapidly as possible. And it's not our fault in the sense, it's just the accident of physics that dark matter can span an extraordinarily large range, and we now have to in fact extend the plot down, because as we move to these sort of next generation experiments, we're currently conducting the LZ and the Panda X 4-ton and the Xenon N-ton. But what we will also be planning to do is to get to the sort of 50-ton plus scale of experiment, where we continue to make very valid particle physics model searches. So I borrowed a few slides from Dan Hooper because I rather enjoyed his talk I attended a few weeks ago. He was really just emphasizing the point, and obviously this is an area with discussion, but that in spite of the fact that we've been looking for 5 or 6 orders of magnitude already, there continues to be reasonable motivation to carry on, because yes, it is correct that the original WIMP miracle exploited the fact that the density of particles, if annihilation cross sections were of the order of the weak scale, that the cosmological universe density would be just so. But it is still, in fact, the case that you can, even in the absence of both in accelerator measurements and in obviously the direct detection, the absence of signal, that we can still reconcile them just simply by suggesting that the models, and maybe this is an example of Sod's law, certainly for those of us looking for direct scattering, of that probability on nucleons is suppressed while you have the necessary rate of annihilation. And there are a number of possible explanations. Now, you may not have gone to them as immediately when originally motivating, but they are perfectly consistent with the bounds that we have at the moment. So, we are covering 5 or 4 or 5 orders of magnitude just in terms of these sort of conventional particle interaction searches, and we do so with a whole range of detectors that are optimized for various range. So let me just focus in on those technologies now, and obviously I'm going to start with the liquid xenon, which is one that's very close, having worked on it for 15 years now. This animation, this is actually for the Lux experiment. The configuration is one that's pretty much repeated through a whole slew of experiments. Obviously, the experiments themselves, the detectors themselves get a lot larger, but in this case, this detector is about 1.5 meters in terms of height as far as the titanium cristat that you're looking at there in the picture. And if we open it, what we have is about 1/2 or 0.6 meters of liquid xenon at minus 100 degrees centigrade, which we are using as a target as sort of an incredibly quiet location. The xenon is very low in intrinsic radioactivity, and if we're careful not to introduce radon as one of our primary sort of backgrounds, you can get a very low event rate inside it. And then we're simply reading out the xenon with a combination of photomultiplier tubes or some kind of photodetector, and also measuring the ionization. And through that, we get exquisite 3D imaging at very low energies using single quanta. Now, what this looks like today is a detector with a linear dimension that's more like 1.5 meters. That gives us nearly 10 tons of operating mass for the target. Yet we are still reading out individual electrons out of the target. Photons, the probability of detection is about 10%. So it's not quite as good as the electrons, where we're getting much closer to 100% detection efficiency, but we see about 1 in 10 of the photons that are generated actually convert them into a signal. And we formed this sort of strategy of multi layers. At Brown, we did actually construct the full photomultiplier tube array, which these days means putting 250 photomultipliers into a very low background frame, which we then drove from Brown on the East Coast here to Sanford Lab. We did this twice because there are photomultiplier tube arrays at the top and at the bottom. This is what they typically look like. This again is repeated across a whole series of experiments, and obviously this was part of a large collaboration with groups contributing. I think we're up to about 25-30 institutions now in the LZ experiment, both US and UK, Portugal groups involved. The overall sort of landscape, if you like, for liquid xenon does have a number of players in it. I already mentioned the Xenon N-ton experiment, Grand Sasso, the Panda X experiment at Jinping. And then, of course, we also have the Argon experiments, which have gone from the sort of 50-kilo dark side experiment. They now plan to implement a multi-ton, probably tens of tons target in the form of this new dark side 20K. On this particular plot, the magenta gives you an idea of where we've been going with the xenon experiments. The orange line gives you an idea of the sort of where the specific sensitivity results from the argon detectors. The intention is of the argon to basically do a huge leapfrog down to sensitivities which are comparable to the LZ and the xenon n-ton detectors using this this much larger tens of ton, 20-30 ton argon experiment. So we do operate them in multiple modes. The conventional scintillation plus ionization, known as S1, S2, that sensitivity, we've been able to push it down to sort of 5 GeV or so, maybe even a bit lower through various techniques. But at that point, we still are able to continue looking for dark matter events using just ionization without the scintillation, and because the effectiveness of collecting those energies is better of the electrons, we can do single electrons essentially. Although the backgrounds prevent us from using that usually for dark matter, but by the time we get 2 electron, 3 electron, we are in very good shape in terms of looking for a signal. And then there's also, you may have heard mention of this before, there's a thing called the Migdal effect, which is where nuclear recoil energy manifests itself in this as if you like shake off electrons, some electron ionization event, and as a consequence we're able to put limits by looking for Migdal signals, limits which are based on masses that are well into the MeV, mega electron volt range. It should be said that Migdal is Migdal needs to be actually calibrated, and that's something that hasn't happened yet, but we intend to do that. Right now we just have to assume theoretically that Migdal is there when setting those limits. This is a plot from xenon 1 ton. It's the last and the best of the last generation of xenon results. There were very similar results from Panda X2 and LARCs, but obviously what you really want to hear about is not the old news but the new news. Now what we know from the experiments is that xenon n-ton will indeed be conducting a science run in 2021. As you might imagine, beyond that, cards are being played very close to the chest. LZ, a similar statement. Science run starts in 2021, very little more information. And also Panda X4 ton has also made a statement that it does intend to be operating, I think, in 2021. But so all 3 experiments are in a very, and of course they will be able to very rapidly move into a new region of parameter space that has not been searched before, so that and all have the goal of improving by well over an order of magnitude from where our current experimental limits are, and through these other techniques, the S2 only and the Migdal should be able to move on. Now, I should mention, because this is new news, but again, it's just more on a experiment thing, but LZ and Darwin have now announced that the researchers in LZ and Darwin have made it clear that they will be working together on a next generation, multi tens of tons detector that's going to push an order of magnitude beyond the existing xenon n-ton and LZ maximal sensitivities, which should be reached up till about 2026. And at that point, it would clearly be desirable to have built and switch on a new detector, which said that is something that we're now working on very directly. And we held a very successful meeting actually back in April now, which is available through that route. So let's talk about some of the other experiments that have been going on. Obviously, I mentioned the argon experiments, the dark side 50, which was the last sort of dark matter search result from the argon, and now the focus on the dark side 20K. And then let's look at the issue of modulation signals. very directly. I think I'd like to focus, well, obviously, Dharma Libre, to mention that it has a 9 sigma, as again, many of you will already know this, it's been running for a long time. Been running for a long time, and you can see, the data has a 9 sigma annual modulation. That was achieved, I remember back, hearing the results all the way back in 97 after a few years of running with 100 kilos, but obviously they switched in 2003 to 200 kilos and have been collecting data since then, hence the 9 sigma significance. I think the thing that critically to understand is that, both the Yang lab experiment cosine 100 and also the Can-Frank Anais 100 kilo, 112 kilo experiment, they have both operated for multi-year, and neither experiment is seeing anything consistent with annual modulation. I think you can get a sort of sense both here from the cosine 100 result here in terms of this being the sort of Dharma preferred region in this standard cross-section mass plot, and this is where the the cosine results are indicating. And then this is another way of displaying it, which is amplitude of annual modulation from NAs. This is where Dharma Libre sits in terms of this 1% sort of annual modulation, or sorry, it's not 1% here. This is counts per day per kilogram per kV, but 1/100th of a count per kilogram per kV. And then this is where the results of the NAs after 3 years sit, and there is incompatibility at the 3 sigma level. And I think I include a graph here which just shows you for first year, second year, third year data, how their sensitivity will increase based on their current configuration. And as you can see, to get, we can get to, after say 5 or 6 years, they can get to the point of certainly a 4 sigma sensitivity and potential disagreement. Well, it looks like a disagreement. That their results are basically just continuing on the trajectory, which indicates nothing. And sorry, I should have mentioned that cosine, obviously 200, the 200 kilogram experiment that's going to be operating at Yangyang soon, has a much lower background than cosine 100, and will be in a position to really test the whether this any sign of this annual modulation whatsoever. Cryogenic detectors, have historically initially were doing well. In the last, say, the 90s and the noughties, they were getting good results on sort of high mass, what we call high mass range. They really now have reconfigured themselves to push into the lowest mass regions, down to the fraction, the GeV scale. I think specifically Super CDMS at Snow Lab is working its way towards operating multiple towers of these kilogram scale germanium and silicon detectors, and if they operate specifically in this high voltage mode, they are able to push, as you can see here, this is 10 GeV, so this is right at the extreme of what the conventional operation, certainly of the Nobel experiments does, although you see here dark side, and also the xenon will push in to the lower masses when operated in the ionization only mode, but you can go much lower with both the silicon and the germanium versions of the Super CDMS detectors, if they're successfully operated in this high voltage amplification of or conversion of electron drift into phonon, Neganov-Luke phonon, which gives you this very low effective threshold. So they can be testing all the way down to half GeV masses. So now must mention what's been happening with the bubble chambers. I mean, it's really this move to the 500 kilo instrument that's excited there. The key was to realize that some of the nucleation of bubble problems, if you like, a high Sisyphean index that existed in the iodine containing compounds, those have been seemingly pretty much eliminated in the C3F8, and what you have is a detector which is at the 500 kilo level that will be installed and operated next year at SNOLAB. And then there is also significant interest in this new scintillating bubble chamber, where you're getting additional discrimination information, because in argon it has been shown that you get a very clear scintillation signal associated with the energy deposition, as well as the conventional superheated bubble formation. I'm not going to talk about directional searches, so let me move straight on to silicon based CCD, and very specifically Skipper CCD technology, which has got us in this remarkable situation now. And I'll just talk about the Sensei, but DARMIC have also been doing very similar, where it's been possible to again get down into the sort of MEV ranges. Now, it should be mentioned that this is talking about dark matter interacting directly with electrons, rather than the dark matter. The Sensei results, and this is achieved with just 2 grams of material, and they are able, through Skipper CCD, to be able to see 1, 2, 3, 4 electrons. So yeah, okay, I should really move to conclusion. Yes. So as I say, we've spent 30 plus years trying to create these sort of quietest known places in the universe. Of course, we really hope at this stage they're not too quiet. We would like a signal to appear in these detectors, but we need to be convinced that it really is signal. Because the massive parameter space, all the technologies have to be ready to scale rapidly in terms of mass. But as you've also seen, we've been really expanding the mass range of particles over which we've been able to investigate. And that has required some really quite innovative technologies. And I only talked about some, some of them. But with every one of them, you have to be ready to realize some have unwanted background pathologies that can fundamentally limit what you're capable of doing. So, I just provide this really as a sort of summary of the current status. But I should mention that obviously, Cosine and NAS are already in a position to really be checking this Dharma Libra signal, which has been around for a long time. Don't see any indication of that signal, and obviously reproducibility is a really fundamental aspect of scientific investigation. So, but we'll continue. The statistical level of conflict is already at 3 sigma. We'll see how much further that goes. In terms of the nobles, I think you've all got the idea that this year, whole slew of 3 new experiments going into new parameter space will be operational, and we can look forward to the results from them. I've also talked about the low mass and a number of the technologies that have really pushed down all the way down to the sort of MEV, if you include the electron scattering. I won't talk about those specific points there, but it is, rare. I will say, after so many years, discovery is extremely exciting, but it is a great responsibility. One has to be very, very careful about how one deals with calibration and interpretation of systematic effects in one's detectors. And you repeat this every time you build a new, bigger detector. You have the challenge, or those challenges all over again. So I think I should end there, and if there's time, I should take a few questions. Thank you.
Okay, thank you for your nice talk. So now it's open for discussion and questions.
I do see a Stefano. If WIMPs interact through, sorry, do you want to say it verbally, or should I read it out? I'll read it out. If WIMPs interact through a spin coupling, xenon and germanium detectors are mainly sensitive to WIMP neutron coupling. No, that's sorry. Yes, I will apologize in the sense that I didn't have time to spin, as it were, into the different couplings. With xenon, 50% of the target is indeed odd neutron, with the majority of the spin in the neutron system. I think, as you're obviously correctly pointing out, a limited number of the targets really have aggressive nuclear spin in the proton. The fluorine, target was always, one obvious or one very suitable choice for that. There is some finite, modest amounts of effective nuclear spin in the proton system in, for instance, xenon. With argon, we have quite a challenge because it is an even nucleus and really doesn't present any kind of cross-section to the spin-dependent couplings. The EFT, effective field theory analyses, which a number of the experiments are doing now, is really been able to generalize when we talk about overall WIMP sensitivity using EFT is the best way to sort of. The only problem is, and why I don't show them, is we end up with 15 different graphs. Well, I suppose 6 leading ones, but I mean, it's so many graphs to have to track. As you might imagine, when we hit signal, it's gonna be fantastic, in terms of being able to, cross compare. And this is why we have to push with multiple targets. You mentioned in your question fluorine and iodine, of course, the iodine and the sodium iodide, the fluorine and the in some of the bubble experiments.
Okay, I have a question. There was a xenon electron recoil excess last year. So
Yes.
do you have any comment on that, on progress on that in xenon Anton or?
Yes, unfortunately, I'm just trying to think. I think I hid the graph on that. No, I'm sorry. I took it out of this deck. Yeah. So no, absolutely. One interpretation obviously is that it is probably due to radioactive argon component electron capture. Although xenon itself says that they think they've controlled for that, and they don't feel that is the likely explanation. I mean, we're now all sitting on entirely new experiments. We've been forewarned about the importance of that part of the energy range. So I think there will be strong focus on it. I usually, of course, when you initially switch on a detector, you do tend to want to, you usually regularize at higher energies and try to make sure that you understand what's happening there. So it may take one iteration of results before you get sort of interesting insights into exactly what's happening down at the the 1 kV, 2 kV regime. It depends. It's always a question of just how well behaved the detector is. Xenon for the most part actually behaves itself. So we may of course you may see that result or comparable results in the early announcements. Okay. But I personally think I'm ruling well, as we pointed out. I think Matthew Sadagas and Cecilia Levy did a very good paper on this. So if you're which is in archive, if you're interested in, and they very thorough examination of the way in which the argon, radioactive argon O7 can sneak into your data.
I see. Okay, so thank you. Are there some questions, some comments? I think
Hi, Richard. Just one.
You have okay.
Relate to the previous questions. So the possibility of the tritium, how do you think about that, and how do you prepare this tritium reduction in LZ?
Right. Well, it because of the way in which we recirculate, you know, and you're worried about cosmogenic production of the tritium, or just some,
or contamination.
That's one of the areas where having a liquid recirculated target actually works very much in our favor. Also, actually, tritium just intrinsically in the xenon is if it's going to end up anywhere, it would end up on the walls of the detector. So it's obviously a lot more of a concern with solid detector configurations. Having said that, of course, we have a terrible problem with other xenon. It's not intrinsically radioactive, and if it is, if we do have an intrinsic xenon it decays rapidly enough, apart from 136 xenon, which of course is a whole rare event search experiment in its own right. But the other noble gases, we spend a lot of time removing krypton from our xenon prior to using it. That's a huge logistic and scientific endeavor. But also radon, another noble, because it leads to beta decay without any kind of gamma tagging. That is probably one of the big limitations on your intrinsic electron recoil background. So you're always concerned about any potential sources of radon, and you are concerned about krypton. But it turns out, we usually remove krypton at source, from the xenon prior to operating. And then of course, as Hyunmin mentioned, of course, argon. Well, sorry, I introduced the argon hypothesis into your question about low energy electron. The argon 37 line, low energy electron capture line is again a potential. So that any of those nobles, because chemically they don't get removed in the same way that a tritium would.
Thank you.
So I think in the case of LG, you still have a low threshold, as low as 1 kV. You still keep the threshold as low as possible.
Yes, we've for decades we've we spend a lot of time designing data acquisition systems that are able to do a very nice job of being able to record every photon, every electron. So they're sort of digital detectors in the in the dark matter regime. It's a bit like running a digital detector. So what limits you always, if you do your experiment right, your signals are huge. What's limiting you is solid state, if you like, or condensed matter. It's a better term. Condensed matter processes that are capable of generating single electrons or single photons. So it's a question. The rates of those, and then the rates at which they accidentally pile up, is what really limits your low energy threshold. But we've been pretty effective about keeping those down, so we can work at this just a very limited number of quanta and consider that to be a signal. It's partly because the TPC signature of an S1 scintillation followed by an electron with a very specific ratio is a fairly difficult signal to fake, and that gives you tremendous leverage over just, for instance, a detector with a single component.
Okay, thank you. So I think we have a parallel session in 20 minutes or so. So I think we had a lot of good discussion during this plenary session. Thank the Richard for his nice talk again. And I'm looking forward to a lot of big large scale experiment for dark matter. We'll find dark matter soon. And the Moore's law is saturated at some point after finding some signal for dark matter. We don't have to do more effort after that. Okay, thank you for your interesting talk, and thank all the speakers in this plenary session. Okay, see you in the parallel session. Okay,
Thank you so very much. Appreciate it enormously.
Okay, thank you. Bye.